Today we'll be looking at the trigonometric functions of the special angles 30, 45, and 60. To arrive at the trigonometric functions of these special angles, we'll be making use of an isosceles triangle for the 45-degree. And here we have this isosceles triangle. And why is this an isosceles triangle? It's an isosceles triangle because this side and this side are equal, and these two angles here are equal. So these two angles on the sides are both 45 degrees. These two angles here, 45 and 45. Why this one is a 90 degree? Because it's a right angle triangle. So we made this one, these two sides 1. This side is 1, and this side is also 1 centimeter. And we have this side as root 2. Well, how did we come about root 2 in this triangle ABC? Well, considering that side AB is 1 and side BC is also 1, this is BC here and this is AB here, yeah, both 1 centimeter in unit, and we said AC is root 2. How do we come about root 2? Well, we know that AB is the hypotenuse of this triangle because it's opposite the right angle here. So it's the hypotenuse of the triangle. So AB square is AB square plus BC square, this is BC here, is going to be equal to AC square. And this is Pythagoras Theorem, which states that the square of the hypotenuse is equal to the sum of the square of the adjacent side plus the square of the opposite side. So the square of the hypotenuse, which is AC square, equals the sum of, as we add, the square of the opposite side, BC, plus the square of the adjacent side, AB. So if we go ahead and do that, we know that AB is 1, so 1 square plus BC square, that's 1 square, it's going to be equal to AC square. So 1 square is 1, and 1 square from BC is also 1. So 1 plus 1 equals AC square. So 2 equals AC square. So if 2 equals AC square, what is AC? We have to find the square root of both sides. So if we find the square root of 2, we'll find the square root of AC square. The square cancels square root. So AC equals square root of 2. AC equals root 2. And what we just did here from AC square equals 2 is just like saying x squared equals 5. If someone tells you that x squared is equal to 25, not 5, so sorry. Someone tells you that x squared equals 25, how do you find x? You just find the square root of both sides. And square root of 25 is 5, so that means that x is equal to 5. So if someone tells you that AC squared equals 2, so AC will be equal to square root of 2. So AC equals root 2. So that's why we have this side here, the hypotenuse of this triangle, to be equal to square root of 2. So now that we have all the sides of a triangle and you know how we arrived at each of these sides, we can now find the special angle 45 degree from this triangle for the sine, for the cosine, and for the tangent. Now remember, in one of our previous videos we discussed SOHCAHTOA, and we said SOHCAHTOA is just an acronym, a short form of knowing what the sine, the cosine, and the tangent stands for. So in this triangle, because we have two angle 45s, we'll only use this angle 45 here to avoid confusion. So this will be our reference angle 45, the one up here. So sine 45 degree, we know that the sine of an angle is equal to the opposite side divided by the hypotenuse side. So sine 45, so sine 45 here will be equal to the opposite, which is 1, divided by the hypotenuse, which is root 2. So sine 45 equals 1 over root 2. So this is the special function for sine 45 degrees. That's the third form. When you write it as a third, it's 1 over root 2. So that's sine 45. How about cosine 45? We know that cos or cosine is equal to adjacent over hypotenuse. So, and the adjacent side of this angle 45 is this one here, and the hypotenuse is √2. So cos 45 degrees is going to be equal to AB, which is the adjacent side, over AC, which is the hypotenuse. So that's going to be 1 over √2. Same thing as the sine 45. So sine 45 and cosine 45 are the same. How about tangent 45? We know that from TOA, the acronym for tangent, we know that the tangent of an angle is the opposite over the adjacent. So tan 45 degrees equals the opposite BC, because BC here is opposite this 1 is opposite this angle 45, our reference angle here. So BC over AB. So AB here, AB is the adjacent to this angle 45. And both of them are 1. So tan 45 equals 1 over 1. So tan 45 is 1. After explaining how to arrive at the trigonometric functions for special angle 45, we now wish to show how this can be done for the angles 30 degrees and 60 degrees. And to do this, we'll be making use of an equilateral triangle. In the previous example, we made use of an isosceles triangle, which is an angle that has two equal sides. But in this example, for 30 degrees and 60 degrees, we'll be making use of an equilateral triangle. That's a triangle that has three sides equal, as you can see from the diagram here. All three sides are all 2 centimeters in length, and they're all 60 degrees. But to arrive at 30 degrees, what we do is we divide this triangle from here and draw a perpendicular line all the way down to the bottom. And when we do this, it splits this angle 60 degree to a 30 degree. So we have a 30 degree here. And if this side is 30 degree and this side is 60 degree, what will be this angle? It has to be 90. So this is a right angle, because the total sum of angles in a triangle must be 180. So in this other triangle that we just made here, this side is 60, this side is 30, so that's 60 plus 30 is 90. So this side has to be 90 for the total sum to be 180. So having said that, we now have the second triangle here after dividing it into two from using a line drawn from the top here. So now we have an angle 30, we have an angle 60, and we have an angle 90. How about this side here? How did we arrive about this side? Because in the initial triangle we only said we had sides 2, 2, and 2. So how did we come about this √3? Well, if you look at this triangle closely, you'll see that this side here is the hypotenuse of the new triangle OAB. So the hypotenuse is 2. And this side here, OA, is 1. And this side, we don't know what this side is. Let's assume we don't know what it is. But we know that this is a right angle, so we can use Pythagoras Theorem to find the missing side. So if we use Pythagoras Theorem, we'll have AB squared, which is the hypotenuse, equals OA squared, which is here, plus OB squared, which is here. So if we go ahead and write those things down, we know that AB is 2 from the initial diagram. We know that OA is 1, because when we divided this side into two equal parts using this line, we divided this side into two equal parts. This side became 1 and this side became 1, which is what we have in this little triangle down here. But OB, we said we do not know what OB is. So AB squared equals OA squared plus OB squared. AB is 2, so 2 squared equals OA, 1 squared plus OB squared. So 2 squared is 4, 1 squared is 1, and we have O plus OB squared here. So if we move this 1 to the other side, we have 4 minus 1 equals OB squared. 4 minus 1 is 3. So 3 equals OB squared. OB squared equals 3. and OB will be equal to root 3 when we find the square root of both sides. So now we've established that OB is root 3. So having known the three sides of triangle OAB, which is what we'll be using, we can now find the trigonometric functions for angle 60 degrees and for angle 30 degrees. So recalling our SOHCAHTOA, as always, that's what we'll be using. So for sine 30, which is, we have 30 degrees here, sine 30 will be OA, which is the opposite to 30, over AB, which is the hypotenuse, because it's opposite this right angle. So sine 30 equals OA, which is 1, over AB, which is 2. So sine 30 equals 1 over 2. So sine 30 is half, or you can say 0.5 if you use a calculator. Cos 30 is going to be adjacent, which is root 3, over hypotenuse. Remember, cosine function is always adjacent over hypotenuse using the acronym CA. So cos 30 equals root 3 over 2. How about tan 30? Tan 30, using the acronym TOA, we know that the tangent of our angle is the opposite, and the opposite to angle 30 here is 1. So 1 over the adjacent to angle 30 here is root 3, because it's not opposite to it. So tan 30 is 1 divided by root 3. How about sine 60? Sine 60 is going to be opposite, which is root 3 here. Root 3 is opposite angle 60, over hypotenuse. Our hypotenuse is 2. Hypotenuse is 2. So sine 60 is going to be OB over AB, which is root 3 over 2. How about cos 60 degree? Cos 60 degree is going to be adjacent to 60 degree, which is 1. 1 is adjacent to 60 degree over the hypotenuse, 2. So 1 over 2. And our tan 60 is going to be opposite of 60, which is root 3. So opposite of 60 over adjacent of 60 is 1. So tan 60 equals OB over OA, which is root 3 over 1. And root 3 over 1 is just root 3. So if you notice, you see that cos 30 degree, sine 60, oh sorry. If you notice, you see that sine 30 degree equals cos 60 degree. Sine 30 degree equals cos 60 degree. They're both half. And you also notice that sine 60 equals cos 30. Sine 60 degree equals cos 30 degree. So they're both root 3 over 2. Also, you also notice that tan 60 is the inverse of tan 30. So tan 60 is 1 over tan 30. So notice tan 60 is root 3 and tan 30 is 1 over root 3. So tan 60 is 1 over tan 30. So they're both inversely related with tangents, special angles. And also you notice from the previous slide that sine 45 was equal to cos 45. They were both equal to 1 over root 2. So these are the special angles. It's very nice if you can master them. Or if you forget any one of them, you can just recreate them if you remember these triangles, the equilateral triangle and the isosceles triangle we used for the 45 degrees.